I would encourage that if you have any doubts, please interrupt me and ask your doubts. Okay. So what I'm going to do today essentially is that as we all know, generative AI and in particular, after Chat GPT, LLM, and also text to video, it's in everybody's mind. So now, in this session, in this 1 hour, I would like to cover that, what it takes to build those model, right? And what are the options do we have to fine tune this model? And when I have used the word fine tuning, I have used it in a generic manner, and I'll tell you that instead of fine tuning, what other options are available. One example is p tuning that I'm going to cover, and also I'll show you the framework which NVIDIA has to offer in this field. The reason being, and what kind of and how NVIDIA framework essentially helps you to build the end-to-end pipeline, and that too of the enterprise grade. Okay. So, so what I'll do first. First, I'll share some of the slide, right, so that I'll set up the context, and in the second half, I would essentially show you the code and how you can also experiment with those code, how you can also run those code, right, so that you're able to get these things in practice, right. So that would be the intent. And so let me start with the first with some background, as I mentioned that first I'll be covering some fundamental concept which will enable you to to grasp the code essentially which I'll be sharing. Okay, and along with that I'll also be telling you the sources, the GitHub link where you can go and try out this thing. You can pull out the container and work in those containers, right? Uh, okay, so let me share my screen. So first I'll start with the NEMO framework essentially. Okay. So what NVIDIA has to offer in generative AI as a platform essentially is a. So I hope my screen is visible. Please confirm. Yeah. Okay. Great. So see, with generative AI, especially with the GPT architecture 3.5 and now GPT architecture 4, and this generative AI has captured everybody's imagination. And now, considering that, we need optimal solution, and also not just just one part of it. Rather, it should be able to solve end-to-end problem statement of an enterprise. So that's where NVIDIA's offering comes into picture, and we call it. It comes under NEMO framework. NVIDIA calls it NEMO framework or large language model services. Okay. So some of the things, some of the overview, what it is capable of, I would like to highlight that. It's capable of and it's capable of text generation, which essentially is that GPT being a auto-regressive model, right? It's excellent in the generating the text. That is the text generation, and also NMT translation, and similarly the coding part, the codex coding part, and also the image generation. If you provide the text, generating the images, and not just that, NVIDIA also has to offer the framework. We call it Mega Molbart. Essentially, that is for the if you give out the the protein sequences, or and to be more precise, the genetic sequences, it will predict the protein structure. So essentially, from the input text, the prediction of 3D structure will happen. So you can think of it as a large language model which predicts the molecular representation. Right? So these are the wider themes which NVIDIA platform has to offer. And in the coding example, I'll take out one particular piece of it, and I'll also show that how you can experiment with that and how you can actually build your solution upon it. Okay? So as I mentioned, so NEMO service or NEMO framework. So it is for the large language model. If you want to do anything with the text to text, right? Whether it could be summarization, whether it could be question answering, whether it could be, you can think of use cases, blog writing, poem writing, all kind of use cases. It comes under the NVIDIA NEMO service, right? If you want to do something on the drug discovery side, where you want to predict the molecule structure, it comes under the NVIDIA BioNeMo service. And if you want to do something on, let's say, from text to image, or even text to video, text to image, text to video, and also text to 3D, right? Text to 3D assets, that comes under the NVIDIA Picasso service, right? And NVIDIA has an option where you can actually do NVIDIA NeMo service on the cloud, Microsoft Azure being one example, GCP, right? And you can do the same thing on-prem also. So if you have your own data center, because of, let's say you have a, if you are working in enterprise where there's a restriction that, you cannot take out your data on the cloud. There we have interacted with enterprises which do have those kind of restriction because of the sensitivity of the data. So the same thing is available as a part of NVIDIA NeMo framework also, right? And some piece of it is available on the GitHub, which I'll show you, and what all components are available, right? So when I say the framework, so it actually helps us to build end-to-end pipeline, right? So when I say end-to-end pipeline, which is not just limited to model, but also once we have extracted model, how that model can connect to enterprise database and give us the desired result, right? So that's the meaning of end-to-end framework. And also generative AI has the some of the drawbacks also, despite it being capturing the imagination of almost everybody. It has the downside, for example, giving out the wrong information, hallucination, people call it, right? Toxic information, out of domain word generation, out of domain answering. Those kind of thing has to be filtered out before you give out the result, so that it can become enterprise grade, right? I mean, with those kind of answers, with those kind of solution, the general public can be happy with that. But when it comes to enterprise grade solution, those things we have to cut it down, we have to minimize, right? So that's where this whole framework comes into picture. So now let me just dig deeper that how that is possible, right, through this framework. And so the first thing is that it helps you in the data curation. And when we talk about any framework on NVIDIA, and in this case is for large language models, so you can think of it being accelerated. Every piece of it is accelerated, right, on GPU, so that you can expect it to be faster, or whether it's on the training side, whether it's on the inferencing side, right? So let's say the first step of it would be your data curation. So even in the data curation part also, because that's the data pre-processing, it provides tools which helps you to curate the data set. In this example, since we're talking about NeMo, NVIDIA NeMo framework, it's the text data. And once you have curated the data, it helps you, the framework actually makes life easy when it comes to distributed training. And as you are aware of that, these models, large language models, right, they are like ranging from some million parameters, it goes to 530 billion parameters, right? And those kind of model training, often it requires not just multi-GPU, but it also requires multi-node, multi-GPU kind of training setup, so that we can train that model in a realistic time frame, right? So, so if you'd have done the programming with, let's say, PyTorch, DDP, data distributed parallel, or even model parallelism, so doing that is not as straightforward. It requires some kind of I would not say expertise, but rather some kind of comfort level with that. But this framework essentially makes this life easy, that you can do different kind of parallelism, whether it's a data parallelism, whether it's a model parallelism, because model parallelism becomes a necessity when it comes to large language model, right? Because let's say if your GPU memory is, for example, let's say 16 GB, right? And if you're the model that you're training itself is a 40 GB, then we cannot put that model in one GPU. We have to slice the model and put that into different GPUs, right? So that we can either train or do inferencing, right? So that's where distributed training part of it comes into picture. And then when it comes to the model customization part, and that's where I'll focus more once I explain about the end-to-end pipeline, that the model customization, we have various options to do that. I mean, one straight away option is that you just fine tune your model, but that is costly affair, right? And that requires a good amount of data set, because model itself, let's say, for example, GPT 3.5, 175 billion parameter model, if you want to fine tune this model, you need huge compute resources, right? So how to minimize that? And also you need a good amount of data set also to fine tune that model. So there have been approaches, there have been innovative approaches, so that we can avoid fine tuning. And and that's where different kind of techniques comes into picture, which I'm going to talk about it. Namely, their adapters, their p-tuning, prompt tuning. So these kind of techniques are there, which actually lets you foundation model adapt to your domain without fine tuning, right? But the fine tuning anyway, if the domain is drastically different, the fine tuning would be required. And once we have done all that, then let's say you get the answer from your model. Now that model has to face the data from enterprise database, right? So that it's always up to date. Correct? So because the model essentially is good at understanding the language, natural language, but how it would know the latest data, right? Latest the information which is frequently changing, that can be faced through a database, and that fetching also has to be some algorithm, some network has to do that, because let's say you are predicting a text, right? And you need to fetch corresponding images or corresponding PDF document or corresponding tables from the data set. So obviously some kind of algorithms, whether it's HDB scan, whether it's some kind of clustering, or whether it's a neural network, it has to be there, or as simple as embedding match, right? Those things has to be there so that it can fetch the right set of data set. And also at the end, while inferencing, it also should be able to, remove the things which are not relevant for that domain, or something which is toxic, and the hallucination, right? I mean, since it's generating, and it might generate something which is not acceptable. So how to remove those kind of thing, how to cut down the downside of Gen AI. So that's why NVIDIA guardrail comes into picture, which actually, takes care of this aspect. And then you can actually connect this pipeline to your enterprise application, right? And so that's how this overall flow looks like. Okay, so so what kind of model under this NEMO framework, let me say what kind of model you can expect, right? So when it comes to the language, NVIDIA has to offer, so we have encoder only model, which is, the BERT-based architecture. And so basically we know that people, since you all are, familiar with NLP, so you might be definitely aware that the BERT architecture essentially is a encoder only architecture, right? Of the transformer part, and it excels at when it comes to natural language understanding, NLU part, because it's bidirectional and looks at the both contexts, right? So the BERT kind of architecture is also is part of this NEMO framework. And decoder only architecture, for example, GPT, right? The different variants of GPT, GPT-2, GPT-3, GPT 3.5, they are essentially the autoregressive kind of architecture, which excels at the generating text, right? Uh, and also there are architecture which are essentially encoder decoder architecture, which requires encoder decoder use cases. For example, classic transformer architecture, it was encoder decoder architecture. Then you have T5. So all popular architecture, you can see that is a part of this language model, right? So when I say being part of NEMO framework, right? So what is the advantage? I mean, you will say that, okay, these architectures are available, other places also. What is the, what's big deal here? I would say, what is the big deal here? Because let's say you want to fine tune the GPT model, right? And you want to fine tune that in an efficient manner. You need a framework so that as a data scientist, you don't have to bother about, model parallelism, how to achieve that efficiently, right? And how to efficiently utilize your GPU, right? And also how to make once you have trained that model, how you can make your inferencing faster, right? How you can compress the model size. So, and there's a framework for that also. We call it faster transformer, so that you can, latency you can reduce. So this framework essentially provides you all of these facilities, right? So that for a data scientist, the programmer, the life becomes easy, and the framework supports that. Similarly, for image, we have diffusion-based models only, but in this series, I would be covering more on the text part. But just to introduce you that NVIDIA provide diffusion-based architecture, clip-based architecture as a part of its, generative AI framework. So now coming to, so when I said that, accelerated training with NEMO, so what kind of things are possible that you can do that? Data curation tool, right? You need to, and also that too in the accelerated manner. We need to, because usually the number of tokens, right, that we need to use. If we are doing from scratch, obviously it will be huge. If you are doing fine, if you are fine tuning it, it will be relatively less. And if you are doing p-tuning, then it will be very, very less, right? And but the data curation tool is a part of this framework. Similarly, for accelerated training, I was mentioning that there are two aspects. That model parallelism, data parallelism alone will not work in case of large language models. It will work if you have let's say GPU with a good memory, 80 GB memory, A100 or H100 GPU, which is the state of the art H100 GPU. But if you have, let's say, GPU with 16 GB memory or less amount of memory, then you have to rely upon the model parallelism, right? And if within model parallelism, there are two ways. There's one thing is called tensor parallelism, and one thing is called pipeline parallelism, right? So the difference between these two, let me just to give you the background, because even if you're fine tuning the model, and if you're if you are basically fine tuning the model, or training from the scratch, this will be basically will be very much useful, right? So uh, if you see this two kind of parallelism, one is a pipeline parallelism. Basically, you split your architecture. You see the Caesar sign. You split the architecture, I would say, vertically, so that a different portion. If you see two sheds, rely upon they resides on different GPU, and the other is the tensor parallelism. Essentially, when you cut down your architecture LLMs, essentially horizontally, right? So what is happening that essentially whole matrix multiplication, the whole matrix itself, you're cutting it and putting that into different GPUs, right? So these are the different varieties of model parallelism. There's a combination of these two also, sequence parallelism, right? Which actually takes a good thing of all these two parallelism. But doing that, I mean, I just explained that already, but doing that, doing that on your own actually takes a lot of effort. So that actually this framework, there's one aspect of this framework which I was mentioning about, is that actually it provides these things seamlessly to you, right? You should be able to, that's why training the model or even fine tuning the model using model parallelism and data parallelism anyway is available as part of it. So you can use data parallelism if you're, the way we typically traditionally use DDP, data distributed parallel, combine that with the model parallelism, right? And you can use, and other than that, there's another technique called selective activation recomputation, right? And why these techniques are useful, because if you are so in case of large language models, and if you want to fine tune it, so we have to be memory selective, right? Because you know that the model itself takes lots of memory, right? And when you're doing this backprop or fine tuning those models, right? So during that, instead of saving every checkpoint, it's advisable to, in this technique, essentially selective activation recomputation, you actually sample the checkpoints which you're gonna save it, so that's how you save the memory on the GPUs, right? And what you do, since we have sampled the checkpoints, now what we have to do when we are recomputing, then we have obviously, since we have sampled it, so we need to recompute, right? Because we don't have every data point. So what we do, essentially, we basically decrease the memory use at the cost of some fractional additional compute, right? So since you have sampled it, so you saved the memory, and now since you have saved the memory and you have only samples available to retrieve the other point which was missed, we need to compute it. So it's just like kind of trading off with compute. You're saving the memory. So all these techniques essentially are are very much useful when we train or fine tune large language models, right? So we have to be careful of using this memory. Otherwise, you'll be getting out of memory error essentially for large language. You will not be able to proceed, right? So that's why. So this framework actually provides you all of these good things that I was talking about as part of it, and I'll show you in the code also, right? And then let's say another thing, what else you can do is that you can do supervised fine tuning with the model, the way GPT-3 if you see GPT-3 architecture and then it became GPT 3.5, the difference was essentially, one was the SFT, supervised learning, that was, and the second thing was that reinforcement learning from human feedback, right? But that was on the data set which was available over the web, right? But if you want to build something like that kind of language model for your company or for your startup, or as a student you want to do on a specific data set, right, which is not available, then you need some framework should provide those kind of capabilities. So this NEMO framework essentially provides you this also, reinforcement learning from human feedback. So let's say once you have your base model, foundation model, you have taken any foundation model, you have fine-tuned it also, and then you can actually use reinforcement learning, which is based upon human feedback, and uh, upgrade your model essentially. And then there's another key thing which I'll dig deeper, that is prompt learning. Basically, in this, what you do, that you do not touch the model parameter base foundation model parameters. Rather, you basically train the prompt embedding, right? That is the concept of p-tuning. Why people use this? Because since you're not fine-tuning the model parameters, now you're essentially you are adapting model to a different task, obviously related task, uh, without touching the your model. So advantage is that you don't have to you don't need extra compute, and obviously the time taken to achieve this will be very, very less. And this part actually we will be seeing through the code, the p-tuning part. And another technique is called adapters, right? I will not go deeper into adapters, but just be aware that adapters is also state of art architecture that people have come up with, different kind of adapters, so that you do not touch your language models, large models, let's say something 12 billion, 530 billion, or I mean whichever size. And you basically in between the encoder and in encoder blocks, transformer blocks, essentially you put residual connections, and also you put MLP, right? Multi-layer perceptron and residual connections essentially. So that part only you train, other thing you freeze essentially, right? So through adapters, you can actually adapt your foundation model to a different kind of domain. Let's say your foundation model, and which actually, for the example, GPT 3.5, 175 billion, it is trained upon, we know that crawl data set and books one, book two, open. I mean, data distribution already available, that on which data set is available. And now, if you want to adapt that model, right? And let's say NVIDIA 530 million Nemo Megatron model, we call it. It's again GPT architecture. If you want to fine tune that for a, let's say, finance or a some other domain, then we can try out what we can try out. We can try out adapters, right? Then so we can achieve that. We can fine tune model for a particular domain at the less compute cost. And once this thing has been done, then it's like runtime information retrieval will also be required, because let's say you ask your question answering system. Let's say you have built, right? You have built a question answering system that that I'm taking very simple example that tell me that what is the weather at this particular time, what is the temperature of a Bangalore or Delhi, Chennai at this particular time, right? So this information, though your language model is able to understand that what you're asking, right? But it does not have the data, right? Because the data is changing. So at that time, you need a language model. Also, you need it needs to retrieve information from the database, which is frequently updated. And for that also, we need some kind of information retrieval network, right? So the framework should provide that. Now, let's talk about what it takes to build those models, right? And fine tuning those models. So for example, GPT-3, that is 175 billion parameter model, right? Which actually is a GPT-3, and it has many variants, right? If you train it on 64 GPUs, 64 GPU, 800 GPU, it will take you 350 days, right? From the scratch. So when I'm saying you need to, obviously it's from the scratch. Fine tuning will take less time depending on how many layers we have frozen, how many layers we have not frozen, right? But if it has to be done from the scratch, it will take so many days to do that. And smaller model, if you see 126 million, it will take 0.92 days, right? I mean, less than 1 day essentially. 5 billion, it will take 9.8 days. But the same model, if you see on the new architecture, which is NVIDIA H100 GPU, it's actually 3 times faster. So instead of, let's say, 9 days, it will take 3 days, right? And what it was taking 350 days, it will take 1/3 of that, because it has a H100 has a transformer engine, basically the hardware level of acceleration essentially. Right? So what it means that since your all this architecture are are based upon the transformer, that block, right? Transformer multi-head attention and all that blocks, essentially transformer blocks. So what this transformer engine does, that is actually there's a hardware level acceleration of that block itself. So that's why you see that gain. But the point I want to convey here is that training this model from scratch or even fine tuning it's time consuming process, right? It takes time. And also there's another disadvantage, I would say, that fine tune the model. If you fine tune the model with the less amount of data set, then it might not, it might not ingest that information, right? because it has seen, let's say, 300 billion tokens. It has seen. Now you are training the model, let's say, with what, 2 million new tokens. That information could be lost. The reason being that model, I mean, it needs more and more data to even memorize that. That's why these additional techniques has come into the prominence, right? Now, let me talk about just one thing, just one thing, this important aspect, pipeline, I would like to talk about. Yep. Yeah, so as I already mentioned that through this framework, and I'll tell you that how to you can play around with this framework and just to have a look at the code of this framework, right? I'll just show you that part also. So let me do this one. Anyway, this thing I have computed. Uh, yeah. So see how this p-tuning thing works, right? And how you basically adapt your model to a different domain. For example, if you take a base foundation model, right? And if you ask that model that what is the yellow part in the egg, the answer will be that this is the part suspended in the center of the egg, right? I mean, this will be the, I mean, since we are just using the foundation model. But if we have to adapt to a different domain, let's say you want to make a nutritional chatbot, or you want to, then the answer will be different, because for the same question, answer will be different. Like, what is the yellow part in the egg? And if you pass it through LLM and we need to adapt it to nutritional chatbot, right? So the answer is, you see the difference. It says that yellow part in the egg is, it talks about fat, cholesterol, and protein, right? Nutrition related stuff. If it has to be, if you want to build a prenatal chatbot which is using this LLM, then answer would be different, though the question is same. Now it's talking about the yellow part in egg is rich in choline, which is important for fetal brain development, right? It's prenatal, right? If you want to talk about something about the food, the chatbot, which is essentially talks about food, then it will talk about the yellow part in egg used to fortify sauce and salad dressing, culinary chatbot. So the idea here is that to achieve this, you do not have to fine tune that model, right? So I hope it is clear, and if not, then please ask me. Let me see the question answer if somebody. Okay. Yeah, I'll talk about that. The what all the foundation models are available. Yep. 43 different kind of foundation model I'm going to show you right now, which is available, and you can have a look. Okay. So the idea, I hope this part is clear, right? So these your different response that you see is without fine tuning the model, right? So when you say the fine tuning model, you are not touching the model parameter. You are just doing the p tuning part, right? And then okay. And then how this p-tuning thing works? So p-tuning essentially works as, you provide input tokens to the model, you freeze the model parameters, and from that prompt, essentially, you make a virtual embedding, and then you pass it through LSTM network. There was a very good paper which actually it has been based upon, and NVIDIA has essentially implemented as a part of NEMO framework, right? And you basically backprop to update the embedding of your prompts, essentially, right? That's basically pure tuning. But your model weights are frozen. So what you're doing, you have taken the foundation model, you have provided the font, you have provided the prompts, right? And that's how you are getting different response, right? So it essentially is a less compute intensive now. Let me just since we are sticking to LLM part, so just let me show you the guardrail, right? How when I was saying that it helps you to keep something, and it keeps you something out of domain word from your answer. For example, you are building something manufacturing assistant, right? Then you need to keep out the biased information, something politics, sport, all those things has to be taken out of it. Toxicity, all those kind of thing has to be taken out. So this guardrail actually helps you in achieve that, right? So when you talk about building end-to-end pipeline, so these kind of thing actually are helpful. Okay, so now let's just have a look over the how it's in action. Okay, so let me open this one. So NVIDIA NEMO as provided as a two option, as a framework and also as a service. Okay, so let me just open it as a can you see my screen? Okay, so NVIDIA NEMO LLM service, right? And you have so you have somebody asked that what kind of models are available, and if you see NVIDIA has these many models, GPT 5 billion parameter, GPT 20 billion parameter, GPT 43 billion parameter, version 1, version 2, and GPT 530 billion parameter, right? So these many foundation models are as a part of autoregressive models are available, right? And BERT and T5 anyway are available, which I already mentioned, right? Now we have option to customize that model two ways, right? You can customize that model either through a API call, or you can do it on, you can do it on our own. You can get that NEMO framework on your data center or in the cloud, or you can do it on an API model also, right? So let me just do one thing. So for example, in this case, and if I show you, see, if you see in this one, and when I say API call, right? So let's say you want to integrate this LLM service, NVIDIA LLM, into your application. So how you're going to do about it, right? That's how you're going to do it. Basically, you once you register for it, and then you will get some API key, those information, and that's how you do. Basically, from LLM API import NEMO LLM, and then you that's how you basically REST API response. You provide your prompt, you provide your model detail, which model you want to query, and how many token you want to generate, and what is the creativity you want to add, different, and beam search parameter, different kind of parameter, and that's how you send the code. So the idea is that you can all of these things which I'm able to do here. Basically you can actually you can see new summarization, extractive question answering, legal paraphrasing, email composition, story writing, chatbot, summarization, structure, unstructured, all those kind of things with a different foundation model you can do. And this is just a playground, but for this you have actually Python API is available, or if you are familiar, your application requires curl also is available, right? So that's actually so as a service, this part is as a service. Now let's say you don't want to use service, and you want to use rather you want to use framework as it is, right? So for that, what needs to be done and how you can get started, right? So the way to get started, and what I have done for this for this today's session for you, is that I'm running my code at I'm running my code at a one machine called DGX A100, right? DGX A100. And if you see, this machine has 8 GPU and A100 8 GPU. So let's see how this machine, that's how you do if you want to see a machine configuration. NVIDIA SMI, you see this, all 8 GPU, one machine is 80 GP, 80 GB, right? And this is like state of the art machine for, training the model with DGX, right? A100. Now, so how you can get started on whichever GPU you are using, if you are on the cloud, right, you can get started. So for that, what you need to do, this link, let me just give you this link, okay, on the chat. Okay, I'll give you LSTM network. Okay, so let me just share that, Mayank. Where should I answer? How type answer, right? So this is for, I think, I'm not, so NEMO framework link I'm giving you, all of you, right? I think it's, and the paper which I'm talking about, this is a P-tuning paper, which is, see this one, I hope this is available, right? See this paper was actually it's from 2021 actually, this paper, and this is a very good paper. GPT understands too, the name is, and this actually NVIDIA has implemented this paper as a part of NEMO framework, right? And if you see this, what I was talking about, that you basically make LSTM network out of it. And if you want, I mean, I just tell you the name of the paper. If you search it, you'll just find it. Or let me just do it for you and send out the link. So if you go to this one, this is a very good paper, and implementation, you don't have to worry. NEMO already does that. But just in case you want to dig deeper, please do that. Okay. How can I chat type? Okay. I think this one. I hope this is clear, right? And everybody, yeah, everybody I have sent a NEMO link also, right? So now let's say NEMO, right? NVIDIA NEMO framework. If you go to GitHub, right? So, and the one example that I'm going to show, so there are two ways to go about it, right? Either you go to GitHub on this page, NVIDIA NEMO, right? And if you go to example, if you see his example, and if you go to NLP, right? And in this one, let me see this language modeling, okay? and language modeling, and there'll be example of prompt learning. Just let me find it. Tutorial, NLP. Yeah, see this multitask prompt NP tuning, right? The nutritional chatbot example I was giving, right? Egg and different answers. So this notebook actually you can also run on your system, right? So this code is already given. Let me just show you. And there are two ways to do about it. Either you take it from GitHub or you do take it from container, which I'm going to show you right away. Okay. So let me just see this one, this notebook, right? I think webinar chat, I have put in the webinar chat, right? So in this notebook, actually it provides you, it takes GPT model, GPT. And since for this example, we have taken, so that we make it, make use of time, we have taken model, which is in the million, not billion parameter, but definitely nobody stops us to take in from the billion parameter. And we can do the prompt learning, which I was talking about, right? So let me show you in this notebook what we are doing. So let me, in this one, and let me do this. No, I will not stop it. Or yes, let me stop it. Okay. So what I have done, okay. So what I have done, basically, I went into a container. Okay, let me just exit this container. Okay, so what you can do is that, you need to pull two options, right? One is that you go to GitHub and clone the code. That one option. Other option is that you can go to NVIDIA NGC. Just type it NVIDIA NGC here. And if you go there, you can make your account and explore NGC catalog. You can do it here. And here, what I've done in the container, and you have many models, everything available there. And if you just type Nemo, okay. So if you do in the container, the advantage will be that, you don't have to bother about dependency. It takes care of all the dependency which is required for fine tuning your all kind of language model, right? Whichever model we're talking about, we have seen, right? So what I have done and what you can also do is that do Docker pull this one, right? That's what, let me do that. So, I mean, you can try that also, right? Docker pull. And I'm just putting my password of my server. Okay, so see, I have pulled out this Docker, right? So, and you see this is the, so I'm just showing you the doing container way, right? Now let me run this Docker container, right? Since now we are running this Docker container, okay, let me first clear the screen so that, it becomes easy for you. Okay, now let me run this Docker container. You see this? So we are inside the container now. Why you can see this root, right? So it means we are inside container. Also, what all things are available, right? LS. If you see tutorials, so you see the exam, right? Whatever you saw at the GitHub, right? Same structure is being followed inside the container, right? So two options. You can clone it from here, right? You can clone it from here, and also you can go to the NVIDIA NGC. Let me just give you the link so that you can, refer it to. Okay. Okay. I think should have, okay. I'll just put to chat, right? Host and host and panelists. Okay, it should be everyone, right? I just put it. Okay, right. So I've just put it this one, and question answer also. I'm just putting it type answer. So you can actually search this container, and what you need to do it is like this, what I've done. So you see the structure here. So now we are inside the tutorial. Now let me just run it, Jupyter notebook here. Just let me run the Jupyter lab, right? And now I can go to this one. So what I'm doing that I'm just, putting my IP address here, or I need to just change the port name. Okay, so see this one, if you see this, the code wise, how does it look like, right? See, okay, let me dismiss it first. So we have run this branch, right? And you see this on the, you can also, once you are inside the container, see, I'm inside the lab, you can see this, and you can actually pip install by this so that you get the latest version of the branch. And that's what I've already done, right, for you. So once you do that, dismiss it. Okay, and then this concept which I was mentioning, the prompt tuning and P-tuning. Basically, you provide the prompt and you provide the answer, right? That's basically prompt tuning, and that has to be provided in the JSON format, JSONL format, right? So what we do, a P-tune prompt tune model on multiple tasks at the same time and add a new task to the model that has P-tune task previously, right? So what we need to do, and if you see the code, it should look like this. So we are training a squad data set, right? Squad, we know the classical question answering data set. We have taken a GPT model and we are basically P-tuning that model. Okay, so we need to provide the task name and we need to provide the context and we need to provide the question and we need to provide the answer. That's kind of formatting that we need to keep in mind when we are doing the prompt training. We are downloading the squad data set, which I have already done prior, right? You see this training data set and data set. I have just downloaded data set. And similarly, I have also pre-process. We need to do some pre-processing of the data set. So that script you will find prompt learning squad pre-processing, essentially the tokenization and all those kind of thing that we need to do, right? And once we have done this, so this actually is the main thing, P-tuning model configuration setup, right? And if you see notice the number of lines of the code that you need to write is very, very less because framework is taking care of all those things, correct? So you basically download the example configuration file from here, wget download this one. And so I was saying that in the P-tuning, what we do, we make a pass it through LSTM, act as the encoder. We make a virtual code, virtual tokens, and essentially what it does through whatever task that you define, right? And it could be a single task, it could be multitask. The embedding of those prompts essentially gets modified so that once you adapt your embedding to a different domain, that's why it's able to answer the question. So for example, the egg example that I was giving you, right? The nutrition part of it. So once you have P-tuned it for a nutrition thing, then the same sentence, right? The same question, it will generate different embedding. That's why your LLM is giving you different answer, right? So essentially, it's modifying your embedding of the prompt itself, the question that you are asking, right? That's the whole idea of this P-tuning. You're not touching the model. So for this, and what we have done is that for this example, we have taken this Megatron GPT 345 million parameters model. You see this and how you can do this? I mean, the code I already shown you. I'm running from the Docker, but you can actually, do the same thing from here. A GitHub link, which I have provided. Go to, examples and not examples, go to tutorials. Go to tutorials and go to NLP, right? And inside the NLP, you have this, the one I was talking about, multitask prompt and P-tuning, right? It's just, you can also right away, you can access this code and see this. Whatever I'm doing here on my system, you can see it there also, right? Okay. So let me just open this first. Yeah, you see this. So we have chosen this list available models, and in that we have chosen this model, Megatron GPT, right? Essentially GPT architecture we have chosen 345, and this model will have .nemo because it's a part of Nemo framework, and the architecture is same GPT-3 architecture. Just that for this experimentation I have chosen, which is less parameters, so that we can take less amount of memory. Correct. So we have taken the model, and also we have to save some of the save model, some of the configuration we need to save. Always save Nemo. I mean, all this configuration that we have done. And for P-tuning, virtual prompt style, I was mentioning that we can set two P-tuning specific parameters. P-tuning uses LSTM prompt encoder to predict virtual token. I was mentioning the architecture, and I've shown you. I've sent you the paper also, and you can tune actually how many layers of you want to P-tune prompt encoder to have, right? So see, for this number of layers too that we want, and also dropout you can set, you can global batch size you can set, and the micro batch size also you can set, right? So all those things are just a configuration parameter here, right? And once you do that, then you can actually, Nemo internally uses your PyTorch Lightning trainer. So you can see this code. We have done all this setting. We are also doing automatic mixed precision training so that we can, reduce our training time. Because automatic mixed precision, if you are aware, that uses Apex library, and essentially it's for so that you can reduce your training time, correct? And then we can actually, that's how this your training code looks like. Trainer.fit, the p-tuning code actually looks like. And for this example, I've just run 2 epochs, that's all, so that we can do it in a faster way. But and you see that once you do the inferencing after p-tuning, you'll see the response has changed according to the domain. So you see the number of lines that you have to write in is very, very minimal, right? And that's because you are using the framework, right? And the framework actually takes care of all those aspects, even all those kind of configuration that you would like to play around with. Let's say you want to since your prompt data set, and typically prompt data set, it depends on the complexity of the task. It could be in hundreds, or it could be even 50, 60. That depends, like how much you are altering the domain. That will define your how many prompt data set you need. So, but just keep in mind that it does not change your. It does you have frozen the model weights. It's a another way to I would say that to adapt to a different domain, but it's a very cheap way to do it, right? The time taken will be far, far less than doing that. So this is a sample example that you can try it out, and if you have even GPUs, which is I would say 16 GB RAM, that 16 GB GPU RAM, that should be sufficient. Even, and you can try out even smaller model on that. The purpose is that you can learn about the p-tuning aspect of it. That's what I wanted to. And you see this, I just I did, and as a result of this, some of the data set was generated. And if you do the same experiment on your container or GitHub, you'll be also able to see this some of the results from this one. Okay. Another thing that I would like to highlight is that under this NEMO framework, p-tuning was just one part of it. Okay, but there are other things that you can try it out, learn, and this repository in any way is like for all of you to use. And you see this, I mean, especially if you go to NLP, right? NLP, you have let me just this LoRa, right? LoRa actually is a adapter kind of network, which I was talking about. Adapter, right? Adapter essentially means that it's another technique other than p-tuning. Essentially, it's inserting trainable architecture in between, and with the residual connection in between your uh, transformer blocks, essentially transformer building blocks, right? So, and this another adapters essentially, right? So for you're taking your base model, but you are fine tuning for a more different domain. You understand? So low rank adaptation, it's also, you can see that it implements this paper. If you see this, it is actually just, let me go back again. So this technique is called adapter. This technique is different from p-tuning, and this implements this paper, low rank adaptation of large language models. This is another technique which you can use essentially to adapt your large language model for a different domain, right? And in this tutorial, if you see, this code actually has implemented this paper, and you can just try it out, the same thing. And the number of lines of the code that you need to write is again very, very small. Again, here also we have taken 345 billion parameter model, right? Sorry, 345 million parameter model, but it's your choice. You can choose any other model, but you can use this adapter to fine tune your model to a different domain essentially, right? And if you see the number of code you have to write, number of lines is very, very less. And similarly, the inferencing also you can try it on at this part of this notebook. So these two essentially are the concept which are very frequently and very, very frequently you'll see paper coming, especially in the adapter. You'll see papers coming, very frequently, because people have now large language model. Now they have taken this LLM. Now they want to adapt for their domain, for their use case, right? And they want to bring their own data so that they can make it work for their problem statement. That's why these things have become important, but they do not have enough data or enough compute resource to fine tune it. As I was mentioning, right, fine tuning that model, it takes time, right? It takes time, it takes compute resource. That's why this p-tuning, that's why this adapters has come into the prominence, right? Now I'll take the question since we are at the end of hour. So let me answer some of the question which has been um, uh, can we run this? You can run this notebook on
Mister,
Collab. Yeah, yeah,
sorry to interrupt, just a second.
yeah,
So
please.
before we start taking the questions, guys,
Yeah,
the feedback poll is live. So you can provide us your valuable feedback as it helps us to conduct more such sessions with you properly. Yes, sir, please continue.
okay. You see this now? Okay, I was covering to which part? I was mentioning about, uh, question answering session, right? What kind of questions people are asking? Let me answer
Yeah,
that.
yes, the
Okay.
Q&A section.
Okay. So Q&A section. Let me open that. Can we use can we use this on your GitHub? You can actually use this. You can, Mayank, you can have actually, your own. You have GitHub. You just need to, pull it, and you can use it actually. And the question is, will Docker? No, Docker pull is not chargeable. No, not at all. It's free. Docker, you can, pull the container from Docker, and it's you just need to make an account. That's all. NGC login. That's all. It's not chargeable. You can run this code on Google Colab, because I was just doing on Jupyter Notebook, but the same thing you can, I mean, you know that Google Colab looks pretty much similar to Jupyter Lab, right? You can do on the this thing also. Besides NVIDIA framework, which other framework are available? See, other frameworks also, they have this solution for this one. I mean, similar solution they will have, but this Nemo framework keys to your question. I mean, it has, the one remarkable difference that you have. One is that you have option, either you go via API route or you go via on-prem, and also, the end-to-end pipeline essentially, and also, the end-to-end pipeline starting from data curation to model fine-tuning to p-tuning and different kind of adapters, accelerated inferencing, right? All those kind of are informed networks, so that you can extract that information for your, problem statement are available to you as a part of one framework, right? So that actually helps enterprises to build, this end-to-end solution in a very less amount of time, as compared to, getting the model from GitHub, searching open source, and, try and experimenting. Here you have everything is available as a part of framework, which you can definitely use, right? Uh, Use case where we should use, and which we should use. Right, great. So Dinesh, so sorry, your question, can you please tell us use case where you should, so pipeline parallelism and which should choose tensor parallelism. So see, the tensor parallelism actually has a one drawback. So you have to essentially choose between tensor parallelism or the pipeline parallelism. Pipeline parallelism essentially, if you will use where inter GPU connect is not a cause of concern. So for example, if your multi nodes are connected through a Ethernet, right, or as compared to, and we call it InfiniBand, which is a faster connection, right? In tensor parallelism, so what happens that you're splitting the whole tensor horizontally, as I was mentioning, right? So what happens that you need to have interaction, right, between different compute nodes faster way, so that you can gather the information, right? So if your communication, right, if the communication is a overhead, then you will prefer pipeline parallelism as compared to tensor parallelism, right? You Yes, you can fork, your fork GitHub account. Yep, you can create this environment in the AWS SageMaker. So all of these, so even if you are uh, you know even if you are on whichever, even if you are on whichever cloud, you can actually same thing. I mean, like for example, this notebook, right? Let me just show you this notebook. Even if you are on whichever cloud, this notebook will, any notebook will work for that matter. I mean, on the cloud, you just have a Jupyter notebook, and, or whichever framework they have, and you need to do typical Python stuff, right? That's all. It's just a library that you need to use, right? Framework essentially you need to use. But the thing is that it has so many benefits, which I have already mentioned, that it makes life easy to, um, do various kind of stuffs. Other questions, let me just, text generation is my area, not quest answer. So yeah, text generation, I think Elizabeth, text generation is area that I think for that, all GPT based architectures will be good for you, right? Because all auto-regressive are excellent in the text generation task, right? As compared to NLU task, where it's still, I mean, it's not like that. I mean, if you combine GPT with p-tuning, it does as good as, an LU task, but typically encoder based architecture are good for typically natural language understanding, and decoder architecture are typically used for purely for, create text generation task, right? I hope I was able to answer your question. Okay.
Mm.
Anybody? So you all please connect me with LinkedIn if you think it's worthwhile. So I'll just post it and you can. I mean, this session does not end here. I mean, technically it ends, but you can ask me any question. Just give this reference to give this reference to the talk, and you can
Your
just,
LinkedIn, yeah, your
yeah.
LinkedIn profile has
And
already been shared.
Yes, great. And you can actually, keep on asking me this question if you're stuck somewhere, then you can ask me these questions, and I'll be able to answer. The main point I would like to convey here is that, the main point I would like to convey here is that, see, building this now, since these applications have become widespread, right? People are trying to use in some form or another. Now we need a framework essentially which solves this problem end to end, and also without any restriction, right? You can do the same thing on the cloud, you can do the same thing on, on prem, right? So that kind of, with that kind of flexibility, so this framework actually, provides you. And all, that this all large language model, it requires optimal use of GPU, and that NVIDIA libraries are very much optimized for, each layer NVIDIA has written. So it knows, NVIDIA knows essentially, how to make your model run faster, not just faster, I mean, train faster, even inference faster, so that whatever infrastructure that you are using, you can do at its scale. So that's where this framework helps you to build end-to-end pipeline in a very short amount of time. Right? Thank you so much. If you have any other question, please ask me any open question. Let me answer that if they are. Um, you can fork Mayank. Dinesh, can we create this? Yes, Ganesh. Yes, Dinesh. I have answered this question. Is this AWS SageMaker? You can just Nemo. All our framework are available on different clouds, right? How can I run these? What are the steps and challenges? Is it free? See, yes. So Nemo framework. So there are two versions. One comes as an enterprise version, but some of the functionality that I've just shown you, that you can. It was already available on GitHub, right? Some of the functionality, p-tuning, you saw even the source code, right? You can straight away use it on your data set. But if you need enterprise support and the cloud API, that's different aspect. But for your use cases, whatever code that you see on the GitHub, that you can use as it is on your data set, right? You just need to change your data path. That's all. Thank you so much. Then if you have any other question, please direct at the LinkedIn. I'll be definitely will be glad to answer it. Okay. Thank you so much.